Okay, hi everyone, I'm Zach, and yes, I will do my best to get us out of here for dinner or get us off of talks and onto food. So I'm going to talk today about 3 different projects. I'm going to breeze over kind of high level or with the goal of presenting on our approach to developing, I'm going to call them vaguely human AI systems, at the risk of misusing human AI teams. I'm going to present on our design, development, and evaluation philosophies. With your forgiveness, I'm going to be a little bit hand-wavy on the findings and results, just given the time here. I do link a number of papers with the assumption that you can get a hold of these slides someday. Happy to send them to you, as well as some demo videos and things like that in here. This work is supported by DARPA, hence the vague term on here, decision advantage. And actually, before I start making fun of them, these are my words and do not represent the official position of DARPA or the Department of Defense, now the Department of War. Yes, eye rolling and cringe is the appropriate response. Okay, so decision advantage, I really just wanted to use that to put some context around this. Aptima is a small business defense contractor, and so a lot of the work we do is applied in defense and intelligence communities, but we are really interested in the science here as well. And so I just put this up there to kind of give some context and to help understand where some of this is coming from and being applied to. But a lot of this is the same challenges that have been harped on today and in every AI paper that's been published probably ever. You know, the data challenges, driving insights, data overload, right? Things like that. So I'm going to keep moving through here. I mentioned that I want to talk about our approach or our philosophy to design, development, and evaluation. It's worth noting that that is facilitated by recent advances in compound AI. And that's very broad, and I mean all of it, right? So the protocols that allow multi-agent systems to communicate, that set up the memory, that do all of these different exciting things with AI now, both for application's sake and for improving the performance of AI itself. So I just wanted to call that out here. So broadly speaking, our approach takes 3 components: real world, memory representation, and simulations to develop human AI systems. I'm going to dive into these a little bit more, so not going to spend a ton of time here, but just wanted to call out that we do use validation with human subjects research. We have a human digital twin test bed that we use to do quite a bit of simulation. And then we manipulate a lot of the multi-agent system design in terms of how memory is represented and moved from one agent to another within a system to optimize for different workflows. So with that, I want to talk about these 3 kind of pillars. I mentioned them as design, development, and evaluation. In terms of design, I'm really talking about implementing these systems in workflows. So instead of optimizing for AI performance like accuracy or speed or something like that, we're optimizing for performance within a given workflow. And so then that has impacts on how the system is designed, how the architecture is set up, everything from the memory, as I mentioned, communication protocols, tooling, all of that stuff. And then finally, this is wrapped up with robust evaluation, which we do, again, simulation with human digital twins, as well as human subjects research. And so this loop is how we go about developing the human AI systems that we develop for in this case, DARPA. So the first project I want to talk about is called BioSage. BioSage set out to develop a research tool, and we started this project about 3 months before a lot of the big AI folks dropped some of the deep research tools. But we distinguish ourselves from those in a few key ways. We're not trying to compete on like model performance or anything like that. We never could, of course. But what we do offer is this focus on the workflow. And so when you think about needing a tool to help you with conducting research, conducting scientific discovery, there are a bunch of small workflows that can fit within that. And so for us, we're looking at summarization, debate, brainstorming, and even experimental design. And so we're developing this system to help within those workflows rather than just being the best at finding the right research papers, doing it quickly, translating it the most accurately, although those are important parts of this broader system. Okay, so a little bit about the development here and kind of how the system is set up. This is a multi-agent system, and again, we manipulate this for those different workflows. And just on how we modulate the workflows, it's very crude at this point. This is very prototype. We have like drop-down menus that ask a user or a team of users what workflow they're working on, and we have a number of other drop-downs that help modulate different parts of this. But no real surprises here. We have reasoning agents, retrieval agents, translator agents that all help in the process of grabbing information from a database. In this case, we use RAG from a large corpus, about 500,000 papers in the biology domain. And so we have retrieval agents that pull from those databases, and it all gets thrown through this system and output, again, based on that workflow that we're interested in. And so again, I'm going to be hand-wavy with the findings here. We do have some qualitative evaluation that we did of this, as well as some quantitative. We ran this through a whole bunch of benchmarks that are published in the literature and developed a few of our own as well. And papers are out, so I'll leave that there. But just want to note that we do find performance differences, and both subjective and objective, in terms of the different workflows and how the system helps the team helps the team conduct debate activities, brainstorming activities, summarization, and experimental design. And so we can do those manipulations and find meaningful differences across those 4 workflows. Again, I left this in here for when you get your hands on the slides later. If we were to have time, which would be a miracle, we could watch it, but we won't. I want to talk a little bit about evaluation. So this has also been harped on a lot today. The differences between, I say harped on in a good way. It's been talked about a lot today. I want to talk just very briefly, because it's been mentioned already, the differences between evaluating AI models, agents, the actual workflows, and then teams. I'm going to use the term teams in this case. These are very distinct things, and it's important to treat them as such, and it's important to hit on all of them. So I want to talk about my next project now, which is called MHAT, or Exploratory Models of Human Agent Teaming. This is a human digital twin test bed that we developed, actually in collaboration with a few faculty here at Carnegie Mellon in the Language Technologies Institute. And some of the papers we've worked on with them are linked here and in later slides. So we build human digital twins. We train them on human subjects research data. We have the largest publicly available human team experiment data. It was an experiment done in a synthetic testbed environment with humans, teams of 3. And so we took that data, and we have all of their behavioral data, their communication data, as well as the environment data from the synthetic environment that they performed all these tasks in. We took that, built human digital twins of those participants, and then we can use this test bed to do all sorts of research and development activities, to test new configurations for some of the AI systems that we're building. And critically, we can manipulate things in those human digital twins. So things like personality characteristics, propensity to trust AI, all these different types of things that we can manipulate. We can drop agents in as well. Critically, we can vary the size of the teams that we're looking at. So from looking at dyads to much larger size teams, which I think is something that doesn't get enough attention in the literature. The meaningful distinctions between looking at dyads versus teams of 3 or 4 or 5. A lot of the findings don't scale cleanly from dyads to larger teams. So this is something else that we can look at as well here. I'm going to, again, breeze over some of the findings. In fact, I'm going to breeze over the breezed over findings just in the interest of time, and talk about the third project, which is called SpiderSense. It is an acronym. Don't ask me what it means. So this is actually a human subjects experiment that we conducted, where we developed another test bed. This was built in Minecraft, where we built a tower defense game. If you're not familiar, it's where the objective is to defend a home base, in this case a tower, from waves of incoming mobs, and they get more complex and more intense as the rounds go on. And so you and your teammates, if you have teammates, are to defend the base from these attackers, and you have to mine resources and build out your defenses and last as long as you can. And the idea is that it gets so hard and so complex that eventually your base succumbs to the attackers. So in this experiment, we had 4 conditions: solo human, 2 human, dyad, Task Voyager, and TARS, which are our two human agent teaming conditions. So in the Task Voyager condition, we built an agent and embodied that agent in Minecraft to be focused on task performance, right? So it gets a skill library and it gets a multi-agent backend that I'll show in just in the next slide, but it's focused on performing the tasks of tower defense. TARS, on the other hand, which you may recognize from the movie Interstellar, the TARS agent is that same task-performing agent, but is given an additional agent in the back end that is focused on team performance. And so we have a number of formal and informal ways of giving it teaming abilities through prompting and RAG and a little bit of fine-tuning that we're just starting to experiment with now. And so the question here is, we hypothesize that diagram on the far right, we hypothesize that human-human team will perform better than the solo human team because we designed this scenario to facilitate team performance. So the question is, what about the Task Voyager and the TARS conditions when we have human agent teams? Do they perform at the level of a 2-human team or a 1-human team or in between? So to give you just a little bit on how we designed Task Voyager and TARS, you may be well familiar with the Voyager paper that came out a few years ago where they built an agent called Voyager in Minecraft that performed by itself discovery tasks and learning and developed a skill library. So we used that same framework, which is open source, and turned it into a tower defense agent. And then, so this is the multi-agent system that lives in Task Voyager. The team LLM on the bottom right there that's in a dotted line, that's the only distinction between Task Voyager and TARS. And so then we run this experiment through dozens and dozens and dozens of trials with naive human participants. And again, I'm going to be hand-wavy with results here. We do find distinctions. We do find performance differences, very interesting subjective ratings of the agents, and we find evidence for overtrust in the agent that had the teaming abilities, giving more trust than it perhaps deserved based on its task performance. Okay, so I wanted to call out our interdisciplinary approach here. My background, which I didn't mention at the beginning, is actually also in IO psychology. I do have some formal training in machine learning and applying supervised learning techniques to psychological research and simulation methods as well. But we really work in an environment with a lot of AI engineers, human factors experts, and this is how we are able to build from the workflow, from that design perspective, through the architectural design features and design the architecture to meet those workflow needs, not just to be the best performing multi-agent system in terms of like accuracy and speed, and then do robust evaluations through things like human digital twin simulation and human subjects research experimentation. So this is really just like wrapping up kind of what I've already said a number of times here, but I did want to leave just a moment to call out a number of my team members. These are my team members internal to Aptima. I mentioned we have a number of other collaborators, including some here at Carnegie Mellon, so just a huge thank you to them, and I'm happy to take any questions.
I abandoned my mic up there, sorry. Thank you. Question?